Hi, this video is on Descartes' Rule of Signs of polynomials. There we go. And I've got it listed out here, and this is a lot of fancy math. For those of you who have fun reading math, you can read through this fully. But the idea of Descartes' Rule of Signs is to be able to look at a polynomial and get a decent idea of how many positive real zeros it could have and how many negative real zeros it could have. And along with that, how many possible complex or imaginary zeros it could have. Okay, so essentially what we're kind of looking at, where does how many times does how many possible places does it cross the x-axis like an x-intercept? Remember, that's the definition of a zero, is where the function is equal to 0, which means where does it cross the x-axis graphically. So that's what we're kind of trying to figure out here with these polynomials. It's a good way to go about it. And when you're searching for roots, Descartes' Rule of Signs is a handy way to just kind of organize yourself and give you an idea or picture of how many of each types of root they're going to be. Okay, so essentially what this is telling us that you might have be given a polynomial with a degree in. Remember, the degree is just the highest exponent of the polynomial. And it says the number of positive real zeros is equal to the number of sign variations of the function, or less than that by an even integer. And then it also says the number of and this is the possible number, okay? And then the number of negative real zeros of the function is equal to the number of variations in sign of the p of negative x. And I'll show you how to handle both of these. Okay, so let's just start with an example here. We're going to start with, let's say, p of x is equal to 4x cubed minus 6x squared plus 2x minus 5. Okay? And what we're interested in, again, is how many possible positive real zeros it has, how many possible negative real zeros it has, and how many possible imaginary zeros it has. Okay, because if you know how many positive and negative, you can also determine the number of imaginary. All right, so let's take a look here. What we're going to do is count sign variations. Now, sign variations means as you go through the polynomial, okay, as you go through this polynomial here, how many times do the coefficients change signs? Well, this is what I like to do. It starts as positive here, but there is a change to negative. Okay, now it's negative, but then again there's a change to positive, and then again from positive it goes back to negative. So that is 1, 2, 3 sign variations. Okay, so what that means, there are 3, and this would be positive, and this is possible, positive real roots. Now, we need to talk about this line, or less than that number by an even integer. Okay, so what we would have to do then, if it starts with 3, we'd have to take away 2 from that. An even integer would be 2. So we'd say 3 or 1. And what this allows for is the existence of an imaginary number on the positive side. And imaginary numbers always run in pairs. That's why we take away an even integer, or 2. Okay, so again, you start with the count, which is 3, and take away 2 until you get to either 1 or 0. Now we check the negative real roots. So what we're going to find is what we call p of negative x. And with p of negative x, what that means is you change the sign of any term with an odd exponent. Okay, so this becomes negative 4x cubed minus 6x squared minus 2x minus 5. And now we look for sign variations. As I go through, I don't see any sign variations. So we say 0 negative real roots. Okay. So now to help me determine the number of imaginary roots, what you have to understand is your degree of your polynomial tells you how many total roots you're going to have. They could be real, they could be imaginary. In fact, the fundamental theorem of algebra tells us that that is the number of complex roots you would have. Okay, so what I do to help me determine the imaginary roots is I like to build a little table. Okay, is to build a table. And in this table, I don't like this table, so I'm going to be a little bit neater with it. All right. So do plus, minus, and I as a heading. And what this table does is helps me put together all possible combinations of positive roots, negative roots, and imaginary roots. Okay, so some rules about the table. First of all, the I column can only have even numbers in it. All right, that's one of the rules. And the rows have to add up to the degree. So if the degree is 3, each row has to equal 3 when you put it together. So now what I'm going to do is in the positive column, I'm going to start with 3. And then I'm going to combine it with the possible negative real roots. In this case, it's 0. Now, if you'll take a look at this row and I add those up, that already equals 3. So that means if there are 3 positive real roots, there'll be no imaginary roots. Okay? Then I do it again. I do 3 with any other, I would do 3 with any other possible negative real roots. But since there's not, I move on now to the 1. And I say, again, there are no negative real roots, okay? And then what I do is I say, okay, well, this is 1 plus 0. That's only 1. My rows have to add up to 3, so I have to put a 2 here in the imaginary column for that to add up to 3, okay? And that is a table that tells me that there could be 2 or 0 imaginary roots, okay? That's what that table tells me. All right, so let's take a look at another example. Let's say now we have the polynomial, and we'll do a fairly decent one here. Let's do 9x to the 5th minus 6x to the 4th plus 39x to the 3rd plus 26x squared plus 12x minus 8. Okay, let's try this one out. So again, the first thing I'll do is determine my positive real roots, the possible number. All right, so notice I'm positive here, so positive to negative counts as a sign change. And then negative back to positive counts for a sign change. And then as I coast through here, I find one more sign change as I go through positive to negative. So that means we have 3 or 1 again, positive real roots. Okay, remember you do your count and then you subtract 2 until you get down to 1 or 0. Now I'll do the negative side of that. I say p of negative x. And so again, that means I change the sign of any term that has an odd exponent. So I say negative 9x to the 5th minus 6x to the 4th plus, or minus 39x cubed plus 26x squared minus 12x minus 8. Okay? So now I count my sign variations. Let's take a look at that. Negative to negative, negative, negative to positive, and then positive back to negative. So that means we have 2 negative real roots, or, again, you remember you have to subtract 2, so you get down to 0. So 2 or 0 negative real roots. This should be an L, okay? So now I'll build my little table again. And sometimes this table can be really big, and sometimes it's just little. Positive, negative, and I as the headings. Now notice this time my degree is 5. So that means we'll have up to 5 complex numbers in this problem. So that means we can have our rows of our table have to add up to 5. And the other rule is, remember, your I column can only have even numbers in it. So if you end up with an odd number in the I column, you've done something incorrectly and you need to check your work. All right, so let's start. Again, the rows are combinations of positive and negative roots. So we'll start with a 3. The 3 could be combined with that 2. So we say 3 positive, 2 negative. Well, that adds up to 5 already, or 0i. We could also say 3 with the 0. Again, we're doing combinations. So 3 or 0, and that adds up to that. Okay, that to add up to 5 again, we have to put a 2 in the I column to make sure the row is consistent. Now we move on to the negative real root. So we go to the 1. The 1 positive real root combination. We move on to that. And we can combine the 1 with the 2. All right. But see, that's 1 plus 2 is 3. So that means there's a possibility of 2 imaginary roots there. And then we combine the 1 with the 0 in the negative column. And that tells me if to add that up to 5, I'd have to put a 4 here. So 1 plus 0 plus 4 is 5. So that means I could have 4, 2, or 0 imaginary roots. Okay. So that tells me those possible configurations that I would need. Let me do one more, and hopefully you guys could get this. Let's try this one. Let me go change my color. I don't like that for this. Let's say P of X is equal to, let's say 4x to the 4th minus 6x cubed plus 2x squared minus 8x plus 4. All right? So we count our positive roots. 1, 2, 3, 4 sign changes. So that means we have 4. Or, again, we decrease by 2's. 2 or 0. So we count down until we get to 0 or 1. That's how it works. Positive real roots. Okay? Then we do our sign change. P of negative x. Okay? So, again, we change any term with a negative exponent. So we say 4x to the 4th plus 6x cubed plus 2x squared plus 8x plus 4. Notice here we have no sign changes. So we have 0 negative roots are possible. So that means in this, if we were to graph this, this would have either 4 x-intercepts, 2 x-intercepts, or no x-intercepts. But it would have on the positive side, and it would have no x-intercepts on the negative side. So now we build our table. Plus, minus, and I. Okay? So we do our combinations. We do the 4 with the 0. So 4, 0. Now our degree is 4, so our rows have to add up to 4. So we put a 0 in the I column. Well, there's nothing else. There's no more combinations with the 4, so we do the 2 with the 0. So we do 2, 0. And again, our row has to add up to 4. So 2 plus 0 plus 2 equals 4. And then finally, we do our final combination, 0 with the 0. And that leaves me 0 plus 0 to add up to 4. That means I have to put a 4 here. So that means I would have 4 or 2 or 0 imaginary roots. Okay, and that's what Descartes' Rule of Signs can tell us. It's handy because later on we're going to be doing some work where we're finding all the roots of a polynomial, positive, rational, real, rational, and imaginary. Okay, so we're going to have to be able to find all of those, and this kind of lays the groundwork as a starting point for that. Okay, have a good day.